And we are live. Hi, everybody. Hi, Stefan. How are
Hi,
you?
I'm doing good. How are you?
I am fine. It's a little bit warm. It's
Yeah,
summer.
it is.
It should be warm. Yeah, and I think it's a great evening for our 21st Rust Linz meetup. Isn't that awesome? It's
It's
hard to
amazing.
believe.
Yeah.
We already have our second birthday.
Sorry, I'm
I
cracking up.
saw that at the beginning you loved my animated GIF, didn't you?
Yeah, fantastic. The dancing crabs is it's hilarious.
I thought this fits perfectly into today's anniversary. Yes, 2 years ago, I think it was, yeah, I don't know the exact date from the top of my head, but it was in August
In
2020.
August, yeah.
We started the Rust Linz meetup in the middle of the COVID pandemic. And yeah, it turned out that it wasn't a one hit wonder.
No,
24 meetups.
that's
Stefan,
amazing. Yeah.
what are your favorite memories if you think back in the last 22 years?
So there are three things right off the top of my head that come into mind. The first thing is our only one in-person meetup that we had so far at the Grand Garage, where it was also summer. It was warm outside. We had a fantastic Ferris cake. So somebody from the Grand Garage was doing a chocolate cake in the style of Ferris, which just blew my mind. And meeting everybody from around up Austria who was speaker at our meetup, finally in person, that was really something. So I enjoyed it a lot. The second thing that comes into mind was our late night meetup that we had around 10 p.m. to midnight, where we connected to New Zealand, and we had two speakers from New Zealand, GT and Tim McNamara, because it was something different. It was late night. I was tired as hell. My jokes didn't land, but still, it was fun. It was interesting, and being able um, to have people from the other side of the world coming to our meetup. That's also fantastic. Third thing that comes into my mind, right after the very first meetup, where Ryan was speaking and you were speaking, I was closing down in the office at Dynatrace. I was home alone that night. So I went directly from the office to my most favorite Italian place and had the best plate of carbonara that I had in my entire life. So that was really fantastic. So yeah, I guess that those are the three top things. But there's so many more. So basically, every speaker that has joined us was a highlight, and I'm very thankful for being able to meet so many people.
Yeah, I fully understand what you just said. While you were talking, I was starting my search engine, looking up the video that we made from our first anniversary with the fairies cake. So if you don't know what Stefan means when he says fairies cake, just check out the link that I just posted in the chat,
Cool.
and there you will see some pictures from the cake we had last time. And speaking about in-person meetups, we have an announcement at the end of this community news. Just stay tuned. We have another in-person meetup coming up, so we're looking forward to that one. Yeah, I fully agree. I took the time today in the afternoon and looked through the videos of all our great guest speakers that we had in the last 2 years, and it was so fun. And I was so I appreciated it so much that so many people took the time. If you take a look at all the videos, we had talks from students. Our youngest speaker was, I think, 14, and
Yeah,
we had
Elvin last
speakers
time.
from all across the globe. We had talks about Nosted development with Intel SGX stuff and WebAssembly and whatever. And I think this broad variety of topics, from beginner to deep dive topics, that is what I value most in these last 2 years. Okay, speaking about what's going on and what's coming, today we have two awesome guest speakers. First one, Ryan. We are so happy to have Ryan because, in fact, Ryan was the very first speaker who was at the Rust Linz meetup. And we asked him again if, after 2 years, he would like to come back and speak again at the Rust Linz meetup. And he said yes. And today he is here. He will kick off the the evening. And the second speaker is you, Stefan.
Yeah, that's
You
me.
will
Sorry.
tell us a little bit. No, we are so happy to have you, and thank you for taking the time to tell us a little bit about Tower, if I can remember correctly, your topic. And we are looking forward to your second talk. If you are not already a member of our Discord server, here is the link to our Discord server. Feel free to join it there. You can ask questions to the Rust Linz meetup about Rust, or you can also ask questions there. We will relay the questions coming in through Discord to our speakers, and you can also ask questions in the YouTube chat. We will also relay the questions to the speakers. So only a few community news left before we go into the first session with Ryan. The first one is, as always, our Coder Dojo Linz, a programming club, a volunteer-led programming club for kids. And we have something which is very special. Stefan, I don't know if you know about that. Tomorrow, we don't have online Coder Dojo. We have an in-person Coder Dojo.
Cool.
We are part of the Innovation Tour Linz, which will happen tomorrow at the Ars Electronica Center in Linz at the main deck. And there we will be present and doing coding and electronic tinkering and things like that with kids starting at 8. So if you live near Linz and you would like to visit the Ars Electronica Center tomorrow, be sure to be there. The whole program starts at 10. Our part is from 11 to 12:30. And in the afternoon, we have another in-person Coder Dojo at a small town near Linz in Willering, where we will have 20 kids between 8 and 12 years. And we will do also electronics and Scratch and things like that with them. So this is the next event that we have in the Coder Dojo. Our friends, female coders, they are currently in the summer break, and they will continue with their events with a big hackathon at the 17th of September. So if you are a woman or a girl who would like to get into IT, or who would like to broaden your personal network in IT, Female Coders is a great community. Check them out. The URL is here. Visit their website, and there you find all their meetings and meetups. The next one, I think I hand over to you, Stefan, because in fact you are one of the organizers. Technologieplauschel is back.
And hopefully I'm also speaking next time. Let's see if I can make it. But we revived the Technologieplauschel a month ago, 2 months ago, to some great success. I guess we had about 100 people or so showing up. It was really missed by the community, and now we are continuing doing it, let's say, every other month or so. And on August 24, we are meeting at Tractive in Pasching. We have 3 speakers, 3 talks. There is a talk about JavaScript runtimes by yours truly, and a talk about WebAssembly. So this might be interesting for all the Rust folks, because those are also topics that we have here at Rust Linz. And Dominic is, I guess, talking about his bee project. Bee as in bees, like flying bees. Because he's, I don't know how I said in English, an Imker, you know.
A purist.
Yeah, thank you. And he tried to create, so he created some IoT things on his own to be sure that they are well and they are collecting enough honey, etc., etc. And he's going to show that next month. So, yeah.
Did you know that I have been an apiarist too for many years?
No, didn't know that.
We had some beehives, yes, and unfortunately we don't have the place, the place to put the bees there. But my father-in-law has bees, so I'm a part-time apiarist now.
Wow, that's fantastic.
Okay, Eurorust is coming up, and Stefan, I think you can also talk a little bit about that, right?
So Eurorust is in Berlin and online. It's a 2-day conference organized by the folks from Simplabs. So I guess there are online tickets and in-person tickets. They just announced the venue, which is the Löwesaal in Berlin, which is near the Zoo district, as I've heard. I'm not too familiar in Berlin, so I couldn't tell you, but it's just a little train ride from my favorite brewery in Berlin, so that's doable. And currently the call for speakers is open, and the fine folks from Simplabs contacted me if I would be able to review proposals and rate them. And there are already many great things that have been that we got through the CFP, and there's still a month left. So if you want to speak at Eurorust, please submit a proposal. There are so many interesting topics they want to hear. And I'm pretty sure that our audience and especially the speakers that we had at Rust Linz have a fantastic content for this conference.
Awesome. Great event. Looking forward to that one.
Yeah, me too.
And last but not least, the last thing, important one, an announcement. We will not do an August meetup. We will shift the end of August meetup, which would typically be our rhythm for the Rust Linz, but we will shift it a little bit to the beginning of September because we have one of the largest festivals for digital art in the world here in Linz, always at the beginning of September, the Ars Electronica Festival. At the Coding Club Linz, we have been a partner of the Ars Electronica Festival for many, many years now. We are offering, again, programming for kids, and we decided to try to organize an in-person Rust Linz meetup at the time of the Ars Electronica Festival. That give all the people who would like to come to Linz and go to our meetup the possibility to not just visit a meetup with two great guest speakers, which we will not announce today, but we will announce them early, hopefully, when we got all the confirmations. But if you come to Linz, you can also spend a day at the Ars Electronica Festival. It's one of the most traditional festivals for digital art. I think they started in the 1970s already. Digital art in the 1970s, I think it was one of the first festivals in that art. So it's really an important thing in the art and IT scene here in Austria. And we simply thought it would be a good idea to combine that with a Rust Linz meetup. And I hope many of you will join us. If you don't have the possibility to come to Linz, absolutely no problem. We will definitely stream. So obviously you can join online, and we will always, as always, record and put the video online on YouTube. Okay, Stefan, I think we are through with the community news. So let's ask Ryan to join us. Hi, Ryan.
Hello.
Ryan.
Hi. Ryan, I always ask our guests the same question at the beginning. Where are you broadcasting from?
I am broadcasting currently from a small island in the North Sea called Pevworm. It's off the German coast, just south of Denmark. So I'm not with my normal setup today, but hopefully nothing will go wrong. Let's press our thumbs, cross our fingers.
We double appreciate you giving this talk. So you are making a break of your holidays and now doing this talk. Oh, that is really, really great. Thank you very much for being with us for the second time. Today in the afternoon, I took a look at the video of your talk from the first visit here at Rust Linz, and you answered a very good question at that point in time. Your talk was about, I think it was Rust and why you should care about it, and it was really eye-opening, super, super interesting. It got a lot of positive feedback, so we are very much looking forward to today's topic.
Great.
Awesome. Ryan, I will bring up your slides. And with that, we will leave the stage. And the stage is yours. Thank you again for being with us. And we are looking forward to your talk.
All right. Thank you. Thank you, everybody, for being here today. I'm very excited. This talk will be quite different from my last talk at Rust Linz. That talk was quite general and about why you should care about Rust. This is a much more technical talk, but don't worry, it's still hopefully going to be very approachable and open for everybody. We're going to be talking today about Rust before main, as in Rust. What happens to a Rust program before you ever reach the main function? But before we begin, a little bit more about myself. I'm Ryan. I work at Microsoft as a developer advocate for Rust. I'm also on the Rust core team, on the Rust Foundation as a project director. So my life is very much consumed by Rust. I got into programming long time ago, kind of on accident through my job. where I learned that I really liked this stuff. And as I've gone along through my career, I've kind of learned more and more and gone deeper and deeper in the stack. And about 2 years ago, I kind of ended up learning about what happens to a program to get it to execute, which I didn't even realize was a question I had. So let's talk a little bit more about that today. So the journey that we're going to be taking together is to answer a couple of questions. The first question is, what happens actually when we run a Rust binary? What's happening in the computer? What's happening in the operating system? How do we actually get to our main function? What even is a Rust executable? What does that even mean? The answer might surprise you. What tools can we use to inspect Rust executables so that we can look into them? And just so you know, everything we're going to be talking about today is only going to have to do with Linux. But don't worry, if you're a Mac OS or Windows user, this stuff will sort of kind of translate. A lot of the concepts are very similar on those platforms, but they may not be quite the same. All right, so let's talk about my mental model before I learned about all this stuff, about how a binary executable actually runs. So here on the left, we have a binary. And most people know that a binary is binary. It's a whole bunch of ones and zeros. And I imagine that when you executed a binary executable, you just started at the very beginning of the file and you interpreted whatever those ones and zeros were as assembly instructions for the given architecture that you're on. Let's say at the beginning here, we have a load B into A instruction here. And then we go to the next one after that. And, it can move around. We can have a jump here, for instance. So we can jump to another place in the binary. And then we execute again. And that's kind of how executing machine code or binary code works in practice. And this isn't necessarily wrong. It's just a little bit too simple. So if this is your mental model, it's fine. You can keep it, but just know that you're not seeing the full picture when you think of things this way. And we'll explore a little bit more around this. So before we get started, a few tips on how to think about things, how to approach these problems. First of all, it bears to be repeated, computers are not magic. There's nothing necessarily magical happening here. It's really all just kind of engineering at the end of the day. That means all of this is ultimately understandable. It may not be obvious at first, and you may not get it without kind of putting a lot of effort into understanding it, but it is understandable. It's not magic. It's not something that you have to divine from the stars. It's all there for you to understand. Everything you see here was made by humans. It is a deliberate choice. It didn't have to be this way. It just ended up being this way. Some of that is because of deliberate engineering choice. And some of those choices you could argue were good choices. And some of it is just kind of random circumstance. An engineer working on something kind of had to make a decision. And they said, well, given a couple of choices, I guess we'll go with this one. There weren't really any good reasons for that decision, but they made it. And now 40 years or 50 years later, we're kind of stuck with it. So don't just assume that if you see something that's funny or it doesn't look quite right, it's because you don't understand it or you're not smart enough. It might simply be because it's kind of just random. At any given point, it's not always easy to tell which between deliberate choice and random circumstance a given decision might be. And unfortunately, out there in the world, some explanations are not always the best. So just because you don't understand something doesn't mean that you're not smart enough. It might be that the person just doesn't want to explain it very well. So don't give up. Before we begin, I'd like to talk through the Rust compilation model. And this is vastly simplified and in some ways not even fully correct, but it's important for this talk that we kind of understand how Rust compiles code. So you have some code. Here's a main function printing a wave emoji here. And we're going to pass that Rust code over to Rust C and LLVM. And of course, most Rust users usually use cargo, but hopefully everybody here knows that cargo is the build tool. And ultimately what cargo does is call Rust C, the Rust compiler. And Rust C is a front end that can interpret, parse, and understand Rust code. And LLVM is the backend that Rust plugs into that takes Rust's understanding of your code and turns it into machine code. But what it does, what LLVM ultimately produces, is object files. And these are kind of groups of functions, metadata, and things about your program in separate files, depending on what the particular compilation unit is. Typically, this is at the crate level in Rust. We get those object files. These are not really executable quite yet. They have to be linked together. So we take those object files, we add in a linker, that's LD in the case of Linux often, and out from the linker comes a binary executable or a binary library, a shared library of some sort or something like that. And that is a program that can actually be run. So that's the compilation model. Keep that in mind. That's what happens before we even start to run our program. So what is the program that we're going to use today? It's going to be a very, very simple one. This is it. It's a main function, and all it does is call std process exit with the exit code 0. This simply exits and makes the exit code the number 0, signaling typically success. There's an issue with this program, though, for our purposes. When we compile it and we look at it, even in release mode, it turns out that it's 3.8 megabytes big. That's a little big. Probably too big for our purposes because it kind of makes things difficult to look at and inspect when you're dealing with a whole bunch of stuff. It would be much nicer if we could still have the same Rust program, but a lot smaller. We can do that pretty easily if we go into our cargo.toml file, and under the profile.release section, we put in a couple of nice features that we have here. The first one is strip, that can strip out some unnecessary things in your binary, because your binary includes things like debug information, which, if you're not debugging your program, you don't really need. And some other symbols and things like that can help with tooling, but are not necessary for the actual running of the program. The next one is opt level, optimization level. We set it to Z, which optimizes for size instead of for speed. Doesn't really matter for our program because our program doesn't really do anything anyway. So this shouldn't really make a difference other than make it smaller. LTO is turned to true. That's link time optimization. That gives the linker additional ways to optimize the size of our program. And the last one is panic abort. And if you're not familiar with this, this is simply changing the way that panics work in Rust from unwinding the stack, giving you a nice message with the stack trace and things like that, to simply aborting your program, stopping the program cold. And it turns out that we end up with a program that's 93% smaller if we just add these 4 options here. So that's easy. But 268 kilobytes is still pretty big. And it turns out if you compile a C program that's of similar complexity, you're probably looking at around 15 kilobytes. So can we do any better? And it turns out we can by getting rid of the standard library. So we're statically linking the standard library. We're bringing it in. We're bringing a whole bunch of stuff that we don't actually need because we're not really using the standard library other than to exit. So this program here is even simpler. It actually adds an external dependency libc here, but that simplifies our program by allowing us to only use what we need. We actually define a real main function, not the Rust-specific main function. You have things like no mangle here. You can see no std, no main up there. So there is no main function. We're actually defining a main function ourselves. And we have to define a panic handler as well. What happens if this program panics? Well, we'll just go into an infinite loop. And if we do that, our program is much smaller. It's now 97% smaller than our original program at 14 kilobytes, which is roughly the size of what you would get if you did the same thing with C. So we're in the area. We didn't have to do a ton of work to get there. All right, 14K, much easier to work with. Let's start exploring. But wait, what is a binary executable? So we still don't know. We know it's ones and zeros, but like what shape are those ones and zeros in? And here we're going to use our first tool called hexdump, HD. And we're going to look at our hello world binary and look at the first line. And the clue to what this binary executable is in the very first line of binary code there. And you'll see ELF. Keep that in mind. We can also use the file tool to look. And the file tool is a nice tool that says, okay, give it a file. I'll try and find out to the best of my ability what I think this file is. And the file tool correctly sees that this is an ELF executable, 64-bit. And there's a whole bunch of stuff in here that you don't understand yet that you'll understand a lot better at the end of this talk. So we see this is an ELF file, an ELF file. Okay, that's good. What is ELF though? Well, ELF stands for an executable and linkable format. So that is in the name, kind of describes what it does. It's a format of a file that is executable and linkable. ELF has information both for static linking. That's when we had the object files before, and object files are ELF in the ELF format, and they can be linked together. But it also has information for runtime execution. So our executable that we're actually going to run also is ELF, and the ELF file has information needed to execute that file. ELF is a database that allows us to look up the info we need to run our program. So we can almost query for the information that we need in order to run this thing. Well, it's not really us that's querying for it. It's more the operating system and another program we'll talk about later. The .text section contains our code. So there are different sections in this executable format. We're not going to look into ELF very deeply today. If you're interested, I have resources at the end. But there are sections in this format that kind of divide up the file format. And one of them is .text, and that contains our code. Why it's called text, I don't know. That's kind of a historical incident. Fun fact, though, the common debug data format on Linux is known as dwarf, and that's a play on the fact that ELF and dwarf are related to each other. Okay, so where is our code, though? Well, we're going to use another tool, object dump or objdump, and pass our binary to it with the -d flag on it. And -d allows us to disassemble the text inside of or the code inside of our binary. And you'll see here, we have our main function. It's right there. We see it, we're good to go, all right? But unfortunately, it's not the whole truth. So there's a lot more code here than just our main function. That main function is what we wrote. That's exactly it. It has XOR EAX. That is essentially making EAX register into 0. If you don't know assembly, that's totally fine. Don't worry about it. And then it returns. So it's doing very simple things, but there's a bunch of code around it. And we see interesting things in here that we probably don't recognize. We'll talk a little bit more about that as well. The .text section contains more than our main function. And there are even other sections that contain additional code. So this is just the text section, but there are other sections that contain even more code. So what is this other code? Well, it turns out main is not the entry point for our program. So we've defined main, and we're used to thinking main is where our program starts, but that's actually not true. It's usually the _start symbol is the real entry point for our program. So you can see here in our executable, we've run object dump with the -d to disassemble, and this is our _start symbol here. And again, it's a bunch of assembly. You don't have to worry about what it does. You can just breathe in the non-web assembly here, and we'll talk about what it does on the next page. Okay, so what is it doing here? Well, it's not that interesting. It's setting up the stack. So if you know about the stack versus the heap, there's a couple of instructions you have to do to kind of make the processor happy with your stack. It's moving argc and argv. Those are the arguments that you usually get in main function, typically in C, for instance. Those are command line arguments that you're getting in. argc is the count of them. argv is the actual pointer to them. So it's moving that to the right place. And it's basically prepping the call to libc start main. So you can see third line up there in the assembly, there's a call queue there. And that's call queue is just assembly for call a function. And the function that it's calling is this very weird and ugly named _libc start main at glibc225. If you've ever heard of libc before, that's where that is defined. This is the function, the sort of main function for libc. So let's talk about that. The other main, libc start main. What does it do? It performs initialization of the execution environment. It calls the main function we provided with appropriate arguments, and it handles the return from main. And it does some other stuff, but we won't talk about that today. The function also calls various hooks that allow the user to change startup and exit. So you can actually define things in your binary that run before your program runs and after your program exits. There's a way to do this in Rust, but it's not quite so easy. And there haven't really been, as far as I'm aware, any kind of stable ways to do this in Rust quite yet. But you can, hack the linker to do it. A word on dependencies. We're talking about libc here. We're talking about libc main and stuff like that. But like, where are these dependencies? Is libc like in our binary? No, it's not. So libc exists on your machine somewhere. And in this case, it's in /lib/x8664 Linux GNU /libc.so.6 is where libc actually lives. So it's in your on your machine somewhere, and our program is merely referencing to it, calling out to it. So this is what is called a dynamically linked dependency. It's not statically linked. It's not in our binary. It's living somewhere else. And we're using another tool here, LDD. And what LDD does is tell us what these dynamic dependencies of our program are. And it's important to remember dynamic versus static here. Most cargo dependencies and things like that are statically linked. They're brought into your program and live in your program. So if you're depending on regex or something like that from crates.io, it's literally inside of your executable. Whereas there are other dependencies that live separately. Like I said, LDD can show us binaries dynamic dependencies, and we're relying on libc.so.6. By the way, SO stands for shared object. This is just a term they use in Linux for libraries that are shared across the system. On Windows, you might refer to them as DLLs. So Linux VSDO is the first one there. And this is not super interesting for our purposes. It's basically provided there to kind of cache system calls so that they can be faster. The kernel kind of automatically maps that for us into our program, or it gives access to it for our program. And we've touched on libc, and we'll also touch on LD Linux x8664.so.2 soon. That's a very important dynamic dependency that we have. So stay tuned. Okay, so let's back up. How did we get here? So we're all trying to figure out how we got to main. Well, we start at _start, right? That's where we start. And then _start ends up calling glibc's _lib libc _start _main. And that function then ends up calling our main function. So far, that's how we get to main. We go from our start symbol into libc's lib _start main, and then finally to our main function. So does this mean that we can just call _start ourselves? And yeah, in fact, we can define _start ourselves as well. So before we were defining main, this time we're defining _start instead. And this works all fine, except if you try and compile this, you'll get a compiler error. And it will say, hey, you have 2 _start symbols here. You should only have 1. And that's because by default, the linker puts in an _start for you. So we have to, when we're compiling this program, tell the linker with this -c link arg thing here, hey, don't do that for us. And that's what no start files does. It just basically says, I'm gonna take care of starting, so you don't have to worry about it. And if we do this, it compiles just fine. So that's how we get from start. We don't even have a main function anymore at all, and we aren't even depending on libc anymore. This is kind of the purest Rust program that can run on Linux. But wait, why do we start at start though? Is there something special about _start that the kernel knows about or something like that? Well, it turns out, no, that's not the case. This time we're going to use another tool. This is called readelf. And what readelf does is allow us to read elf and print it out in a nice format so that we can understand it. We're passing -h here. And what -h does is give us the header of our elf file. And the header is a whole bunch of metadata. And the particular piece of metadata that we're interested in is this entry point address. This entry point address is what tells the world where we want to start executing. Where in this elf file should the kernel or whoever start executing this program. And if we look inside of our elf file at that offset that it was 1040 hex, you'll see it's at our start symbol. So the fact that it's called _start is more of a convention than anything. It's really, and it's a convention that the linker takes, advantage of and stuff like that. But from the operating system's perspective, it doesn't know anything about start. And in fact, underscore start is not even really there. It's just a label. It knows about that because of that metadata information inside of the header. All right. Then that begs the question, okay, then what calls start? Is it the kernel that calls start? And sometimes yes. Sometimes the answer is yes. But we need something in addition to just getting started. We need a couple of more services to be done for us. We need something that parses this ELF binary and maps it into memory for us. So we have a whole bunch of code. It exists on disk, right? But like we need it in RAM somewhere so that we can run it, so that it's, and we presumably need to make it executable, because if you know anything about security when it comes to kernels, like not all memory is treated the same. Some memory is readable and writable. Some of it is executable. We need to make sure that everything lives in its right place. How do we get the ELF binary from disk into memory? And then second, how do we load these dynamic dependencies that we have and put them in memory? How do we make sure that they're in our address space? Because they exist somewhere on disk too. So we need something that loads them as well. And we also need a way to ensure that our binary code can call them. So if somebody loads it into memory and our code is there, what address do we call to call into libc? Who does that mapping for us and things like that? Well, it turns out we need a tool called a dynamic loader. And this dynamic loader is also known as a dynamic linker, confusingly. And this is different than a linker, aka a static linker. This is a dynamic linker. And it's also known as a dynamic interpreter. So if you see any of these three names, you know that you're talking about the same thing. Dynamic loader, dynamic linker, dynamic interpreter are all the same thing. And what they do is essentially what we've talked about. Take this ELF binary, map it into memory, load dynamic dependencies, and ensure our binary can call them. The kernel does some of that stuff, and where the kernel starts and where the dynamic interpreter starts is kind of not for today. But we can think of the dynamic interpreter as doing a lot of this heavy lifting for us. So where is this dynamic linker? How does, who's running it, whatever? Well, it turns out our ELF file actually says what dynamic linker it needs to run with. And if we run read ELF and look at the .interp section, which is what -x.interp does for us, then it will show us here that it needs this /lib64/ld Linux x86 64.so.2 dependency. And if you remember back to LDD before, this is exactly the third dependency that we talked about that our binary has. So it was the kernel that put some of our executable into memory, and then looked inside of our binary and said, oh, this thing needs a dynamic loader. Which one does it need? Oh, it needs that one. I'll load that one for it, and then I'll hand it off to the dynamic loader, and I'm out. So really, the kernel has a pretty simple job when it comes to things, and it hands off to the dynamic loader to do the really heavy lifting. Okay, so how do we get here? So we have a dynamic loader that the kernel hands the dynamic loader this executable. The dynamic loader does a whole bunch of work that we're not even going to get into today because unfortunately we don't have enough time. It does things like map memory. So it takes the stuff that's on disk and puts it into the right place in memory. It loads our dynamic dependencies. It does something called relocations, which is a whole nother subject, essentially saying you want to call this function over here. Well, where in memory is it? Okay, I'll basically hot patch your program to be able to call that function in the right place in memory. So if you thought of binary executables as being very static things, I hate to break it to you, there's a whole lot of dynamicness to static binaries. And then eventually, when the dynamic loader is done with everything that it needs to do, it jumps to _start for us. And that's when our program takes over. Okay, so we know how we get to we know how to get from the dynamic loader to the _start symbol, and we know how to get from _start to main. So we're almost there, right? Where at some point we have to stop this madness, and we have to just be at the beginning, right? So what actually invokes the dynamic loader? And that is this xcve call. And this is the system call that Linux provides for actually executing a binary. And as we see here, XCV executes a program referred to by the path that's passed to it. This path must be either a binary executable or a script starting with hash bang interpreter. So, you know, if you've seen that in a script before, then you know where that comes from. If you want to run Ruby or Python or something, that's where that comes from. And basically then that loads it into the kernel, and the kernel looks at the alpha executable, looks at the interpreter named in that .interp segment that we talked about before, notices, okay, it needs a dynamic loader, I'll load that for it, and then I'll just hand it off to the dynamic loader and walk away. And that's it. That's basically the begin. So where does our journey begin? It starts at this system call that is literally what gets called when you're at a terminal. If you're in a terminal and you do / your binary executable name, all the shell does is take the path there and pass it off to this CVE system call. Does very little other than that. And that gets passed over to a dynamic loader from the kernel. That dynamic loader eventually calls _start, which eventually calls _libstart main, which eventually calls our main function. We finally figured out how we get to main. And then all of the fun actually begins. Okay, so what did we learn today? We've learned quite a bit. We've learned all the steps that it takes to get to our main function that we just went through. We learned how to make a small enough binary to easily inspect, because if we do a bigger binary, we're just going to be going through a whole lot more data, and it's all the same thing. It's just harder to work with. We've learned a little bit about the ELF file format. We've learned where our code is and what code is added for us on behalf of the compiler and the linker. We've learned about libc's _libc start main. We've learned about the start symbol. We've learned about the dynamic loader that loads our program, maps everything into memory, moves it around, patches our program for us so that it's correctly callable. And we've learned about the syscall XCV, which allows us to actually invoke the kernel and then get into the dynamic loader. But what did we not learn today? Because there's a whole bunch. This was kind of just the introduction into actually how programs get executed on Linux. We didn't learn about the specifics of libc start main at all. It's more complex than I let on. We didn't learn anything about the exact layout and contents of ELF files, what's in the header, the difference between sections and segments, where things live, different string tables, and things like that. We didn't learn about the full responsibilities of the dynamic linker. We talked a little bit about relocations, for instance, but that's a talk in and of itself. We didn't learn how this works at all on other platforms. What about Windows? What about Mac OS? What about BSD? Lots of fun dynamic loading tricks we didn't talk about. So if you're interested in kind of, okay, how can this help me hack things and things like that, I suggest you look into LD preload. There are a couple of talks out there that I've seen given where people use LD preload to do fun things. I believe there was one by Jan Erik who ended up putting something in LD preload that kind of rewrote all of the libc functions in charge of printing and just caused everything to be uppercased and append exclamation points to it. So you can kind of hack binaries that way, which is really fun. So given all those things that we don't know about, I want to give you some resources to go, because this was really just an introduction. The first one I'll talk about is Matt Godbold's The Bits Between the Bits, which is kind of what got me into this stuff. This is a CPPCon talk that talks about how to get to main for a C++ executable. And that talk goes even deeper than I was able to go in today. So take a look at that one. Then, of course, Faster Than Lines, Making Your Own Executable Packer is probably kind of the best, I would say, Rust-specific introduction or really guide to learning about this stuff. You essentially create your own dynamic loader from scratch, which is really cool. Patrick Horgan's How the Heck Do We Get to Main is really great and gave me a lot of this information. If you're into Windows, James McNellis's Everything You Ever Wanted to Know About DLLs is really fantastic. So you can kind of essentially learn the same thing, but from a Windows perspective. And then John Thagen's Minimizing Rust Binary Size is a great resource if you want to make the smallest possible Rust binary so that all of this is a little bit easier to work with. All right. And that's it. That's my talk. If there are any questions, be happy to answer them.
Thank you very much, Ryan. Thank you. That was a super interesting talk. I learned some of the things in school many years ago, and I remembered some of those things, and I found it very, very interesting. Yes, we have a bunch of questions. The first one is from my side. Is it possible for you to share the slides, especially with working links? You
Yes.
can either put it yourself on the Discord server, or you can just send it to me, for instance, in PDF format or something like this, and then I will share it through the Discord server. Is that possible?
Yes, I will do that.
Very good. So let's go into some questions. I remember that you said at the beginning that you had to do some optimizations to make the size of the executable smaller, because otherwise we have the standard library in it and so on. And in exactly that area, Elvin was asking this question: doesn't Rust only compile or include functions that are actually used in the standard lib?
So that's a complicated question, or more complicated than it may seem at first. No, I'm not 100% sure of the answer. So no, the full standard library will not be compiled with every program. That's certainly true. Or I should say, yes, the full standard library is probably compiled. Let me take a step back. The standard library is provided as a library in compiled form with every Rust distribution. So the compiler doesn't have to compile it for you. It's already been compiled and distributed to you through Rustup. So you already have it. It's really the linker then that can look at that and say, okay, these functions are not being used. We'll no longer include them in that. So yes, for every Rust executable, the standard library has been compiled for it, because it comes in a compiled form, but the linker is able to remove some of that dead code. Whether it removes all the dead code that is not used or not, I'm not so sure. And what is being stripped out at the end of the day is probably mostly debug information and things like that versus code, because really strip doesn't know enough about your program in order to strip the right code and not the wrong code. It's really the linker that will have that kind of information. And without it going into even more detail, even the linker doesn't really know anything about your code. It only knows about sections inside of your object files and whether those sections have dependencies between each other. And if they don't, then it removes them. What that means is if there's some dead code in a section with non-dead code, that dead code will likely end up in your executable at the end of the day.
Okay. I learned something new here too, and Elvi was just writing in the chat again. I didn't know that the standard lib is pre-compiled by Rustup. I didn't know that one. I thought it would be compiled from scratch, but that was an interesting one. Thank you very much.
And in fact, there's an interesting feature that's being worked on, or has been in the works for a very long time now, and is available in the nightly compiler, called build_stud, where you can compile the Rust standard library. Yeah. And that allows you to tweak the Rust standard library. So, for your platform, you may want different, or for your use case, you may want the standard library to behave differently. You can't do that in stable Rust right now. You just have to use whatever shipped with you.
Super interesting. Super interesting. So the next question is this one. It's from, I don't try to pronounce the name here. Is there an alternative to the ELF format? You've spoken a lot about the ELF format. So any options here?
So ELF has been in use in Linux as the main executable format for, I believe, since like 1995 or something like that. So early on in Linux's evolution. There was a binary format called a.out before that. Whether any are used on Linux today or not, I'm not really sure. I've not really encountered any, but perhaps there are. On other platforms, of course, there are other binary formats. On Windows, there's the the PE or COF alternative, which is essentially just like ELF. It has the same type of information in it. It's just laid out differently. It has a couple of different concepts. It has some fun things in it. Like I learned, for instance, every Windows binary has a DOS program at the very beginning of it that, if executed in DOS, will basically run and print out, this is not a DOS executable, and then exit. Because Microsoft takes backwards compatibility very seriously. So that's fun. ELF doesn't have anything like that. But yeah, no, I don't really know about any alternatives on Linux that get serious use.
Okay, interesting. Here we have a question. It relates to the dynamic loader and asks about threading. If the dynamic loader works in the same thread as the app, can you elaborate on that?
Does it work in the same thread? So it is in the same process space. So that's good. We know that it's in the same process, at least. Whether it's in the same thread or not, I'm not sure. I'm not even sure if the mechanism for threading that's a very good question. Threading might not even be a concern that has been set up yet. I know libc does a whole bunch of initialization of kind of thread locals and things like that. So the idea of threads oftentimes kind of may come after the dynamic loader has even done its job there. So my answer will be, I don't believe so. Yeah.
Okay. I would like to add one question from my side. You talked at the beginning about how your Rust program is compiled, and you spoke about LLVM and things like that. And recently, there was some news that there is work going on a GCC compiler backend for Rust. And I would ask you what your thought is about that. What I get asked by people, what does that mean? Why is that done? Why is that important? What are your 2 cents about that one?
Yeah, it's an interesting question. I'm not involved enough in, so this has largely been done for the Linux kernel community, because they have very specific needs for building the kernel, and a lot of their tooling is GCC specific. So it's not like it's a couple of people just saying, well, we kind of don't like LLVM because it has a bad name or something like that. It's nothing like that. It's a very specific tooling need. I think there's another effort going on besides a full rewrite. There's the GCC backend for Rust, so it keeps the same front end and just switches out LLVM's backend for a GCC backend. There's also the full rewrite, where the front end and the back end are completely rewritten and packaged inside of GCC. I don't know enough about the details to have a strong opinion here. At first glance, it struck me as more sensible to only rewrite the back end, because that's really what allows the different tooling and stuff to work. Rewriting the front end additionally is a lot of additional effort, and I'm not fully sure of the gain there. But at the end of the day, we knew something like this was going to happen, and I'm happy to see that the Linux community is being kind of open and really they're communicating well with the Rust project and things like that. So who knows how this will all turn out, but I'm confident that it's going to turn out well either way.
Yeah, super interesting. Thank you very much. Ryan, if you have time after your talk, you maybe can hang around for a few minutes in the Discord server. I've seen that we had at least one off-topic question that is really interesting, and I would ask the user to maybe ask this question in the technical discussions or meetup section in our Discord server. That might be interesting. And also, again, if you would share your slides with us, that would be awesome, because you had so many interesting links to additional material. And I would myself like to watch some of the videos. I didn't know some of them to deepen my knowledge in that area.
Great. Thank you very much.
Thank you very much. Thank you for being with us on our second anniversary. Thank you for this super interesting deep dive into what happens before main. And I wish you all the best and a very beautiful rest of the summer evening.
Thank you.
Thank you. Bye. And with that, I think it's time to bring Stefan up again.
Hi, I'm back.
Stefan, wasn't that an interesting talk?
Yeah, a lot. It was nice.
Yeah, and I see
learned a lot.
clap
I definitely
emojis
have to
came up.
rewatch it again. But
Yep.
sorry.
Yep. Yeah. Super interesting.
Exactly.
And now it's your time, right?
Yes.
Very different
Yes.
topic. I think in your talk, you will not care about what happens before main, but you will talk
no.
about what happens after main, right?
Yeah. So the only thing that happens before main is a Tokyo async macro. That's directly aligned before main. But that's all. That's all I can give. Alrighty.
Okay.
Cool.
Stefan?
Yeah.
I'm looking forward to your talk. Enjoy it. The stage is yours.
Alrighty. So hey, my slides are fantastic. Okay. Yeah. Welcome to the second talk of today, to Introduction to Tower. It kind of struck me after I proposed this and said to Rainer, hey, I do a talk. If you don't find a second speaker, I will talk about Tower because I play around with Tower a lot. That this is basically the sequel to my other two talks that I had at Rust Linz, which were Tokyo Warp and WebSockets, and the other one was serverless Rust. And now I'm kind of combining both. I'm having a couple of things from the Tokyo ecosystem. I'm going to show you a couple of things from serverless, and I'm giving you an introduction to Tower, which is a quite interesting framework. So my name is Stefan. I'm one of the organizers of Rust Linz. This is the worst Twitter handle in the entire world. It's short for Dead Parrot. If you want to reach out or want to chat with me, that's the best way to get me usually. Quick disclaimer up front. So everything that you're going to hear today, take it with a grain of salt, because I'm not involved in the Tokyo projects. I'm not involved in the Tower projects. Everything I learned and everything that I collected here was done by me. So I did a lot of research. I read a lot of documentation. I looked in a lot of forums to see what was going on. Was looking in some GitHub issues, etc., to get myself an image that works for me, and it might work for you as well, and you might be able to ship great software afterwards. But it might be that I get a couple of things wrong. And up front, I'm sorry if I've done that. I'm pretty sure people in the comments are going to correct me, because that's what they do. So yeah, if you know more about that, please tell me and reach out to me. Tower is part of the Tokyo stack. So we have spoken about Tokyo a couple of times here in Rust Linz already, and I'm pretty sure if you've done async programming, you have seen Tokyo and you have done something with Tokyo. Tokyo is not only a runtime for asynchronous programming, but it's also an entire ecosystem that comes with tools for network applications like Hyper, which is a complete implementation of HTTP 1 and 2 for the client and for the server, or Tonic, which is, I guess, the gRPC equivalent of Hyper. And both those layers, Hyper and Tonic, they build up on Tower. Tower is this one box in the middle here, which is basically an abstraction. It's nothing more than it. No, there's a lot more to it, but the core of it is an abstraction to abstract the request response pattern, not only for servers but also for clients. So they got rid of the server name in the abstraction and call it service. And what you can think about is it's basically middlewares. You're stacking middlewares on top of it, and you can reuse them throughout your applications, depending on which applications that you're writing. And I think it's called Tower because you have a tower of services. Again, this is just me trying to figure out how things work. But you have a tower of services that you stack upon each other. And when a request comes to your application, it first goes through the logger, then you log out some stuff, then you check, then you have a timeout check, so your request doesn't take too long. Then it's being transformed into an actual HTTP request that lands in your function, so you can work with it, you can do something with it. And then you send the response back, and there you go. Again, Tower revolves around this service trait, and it kind of looks like this. It has a couple of associated types, and it has two functions that need to be implemented. The first one is poll ready. This gives, if you're familiar with async, it gives you a poll pending or a poll ready. That's an enum that's being used in async programming, which tells you either, well, that the service can be used. I'm ready to process your service or to process your request. Or it's like, well, wait for a second, I'm not ready yet. I can process your request later on. This is great if you have things like queuing or load balancing or load shedding that you want to implement as a service. You can do it with this poll ready function. You can say, wait, I'm full, my buffer is full, please wait until you use me when I'm ready. And yeah, this is the same poll that you get from polling a future. The other one is call. And with call, you are getting the request object, you can work with it, and you return a future again. And most of the time, you're returning an inner future. So services are meant to be wrapped around each other like an onion, with the last one in the middle. And usually you returning the future from the last one, and then again from the inner one, from the inner one, from the inner one, until you reach the outer one. So it's a very simple trait, not that much to implement, but it can get very complex, especially if you want to compose your services later on. Let's look at the very simplified logger service. So what we want to do, we are writing an HTTP application. And what we want to do is that at the moment the request comes in, I want to log a little bit information about this request. Usually I'm creating a struct that is a generic with an inner service. So this is the wrapping, this is how you build up your tower, just services within services. And this is also everything that that logger is doing. So you are just taking another service, you own it, and you compose it. It gets interesting the moment you have the service trait. So here we are implementing the service for HTTP requests with a body for the logger. So this is how we implement the service. And this service, we're implementing it for other services that can handle requests. So I'm talking a little bit more about this in just a second. Since we get requests in and push requests down, we also get responses up. This is what's happening here. And if an error occurs, we're just bubbling up the error from the other service. The return future that we expect, the future that's being called afterwards when everything's wrapped up, is also the future from the service that we wrap. So basically, we're taking everything from this one service. The polling function polls the inner service, so we know if the inner service is ready. And here, that's everything that we do. So the moment this service is called, we say, well, we are processing whatever method at whatever URI and call the inner service. You see, this is an expression, so there's no semicolon in it, which means the inner service is also returning a future. And there you go, everything's wrapped up. This is how a service should work in theory. Not only in theory, this actually works also in production. I've used this a couple of times. It's probably not the best service, and you can do much, much better things with it. But for a hello world, it's nice enough. Let's look at those services in detail. And let's look at those services by implementing an application that should run both on AWS Lambda and Azure Functions. So I want to create an application that is totally independent from the environment where it's running. But I can have a layer that adds my application either to an AWS Lambda invocation or to an Azure Functions server. If you've seen my talk Serverless Rust, I talk a lot about how those different serverless architectures work. Lambda is very special in how it's being invoked and how it gets its tasks. And Azure Functions, which is very, very nice if you want to migrate your app to Azure Functions, is basically a server with some boilerplate code. So it's not entirely true for all of Azure Functions, but if you're doing Rust on Azure Functions, you are just providing an HTTP server and hook it up to the function host, and there you go. Which makes basically every one of your HTTP applications also a fully qualified Azure Functions application, which is nice. The app, as you can see, there's no sign of anything async other than the async keyword here, or anything related to Tower or Tokyo. What I have here is I have a handler function. It gets in an event. So this is the payload that I want to deal with. I wrapped the Server value inside this tuple struct. I don't know why anymore. I guess you just can pass the value itself. That should work also. But I call it event mainly because of the naming. I extract the value here. I see if the first name is here, and I want to say either hello Stefan or hello world or whatever, and also put a value back. So the value is also the result that's being pushed up. That's like you would expect to write a serverless function. I have an error. It's a boxed error. It's that I can consume every error, and it has one dependency on Server. That's everything it is. And I want to take this function and attach it to AWS Lambda and to Azure Functions. For Lambda, I'm writing a Lambda event parser, which is a service. It takes an inner service via generic. So the constructor, the implementation of my struct looks like the one from the logger. That's basically, I guess you can create a macro for that. That should work as well. I don't have any other things that I need to wire up here. It gets interesting once we implement the service trait to it. So this is the entire implementation. It still fits on the slide, which is nice. Let us go through a couple of things there. First, I implement the tower service for Lambda events that carry a CERD value. So this is one generic that I need to fill out. I'm implementing the service. If a Lambda event with a CERD value comes in, then this implementation is valid. And this is what's incoming, and this is what's outgoing. So if you still think as this tower of middlewares, this is what's coming from above and going down to your own function. So I want to convert a Lambda event that carries a value to a service that can carry an event. And this event type is this one type that I defined in my function. There's one thing that a tuple struct with the CERD value. Very similar to the Lambda event, but with less fields and much easier, and none of that Lambda has. So that's that. Since I'm working with values here, both in Lambda and in my service, I can just bubble up the response types and the error types and the future. That's all fine. I don't need to do anything here. So the response will be a CERD value, and Lambda can work with CERD values. Great. And also the error, it's the any error anyway. Bubble it up. That's fine. Now for the call function, it's pretty straightforward as well. I get the request. I split it into parts. That's a function from the Lambda event. I'm taking this value. This is now the value, like the CERD value, wrap it into the event and call the inner service. The inner service returns a future. This is the future node that we defined here, the type future as : future. Give it back. And that's how we integrated our function to Lambda. Now for Azure Functions. I'm writing an HTTP parser because it's not only for Azure Functions, but basically for every HTTP server, which is nice. Same thing. Again, I could possibly write a macro. I wrap a service inside the HTTP parser. However, it gets much more interesting when I look at the types that I need for implementing the service. So I'm implementing a service for an HTTP request with a body. So this is all from the Hyper crate. Where? So this is again incoming. This is there's an HTTP request with a body incoming to your service. Now please unwrap it. And I want to send it, this line, to again a service that swallows my events, that takes those events that I have defined within the app, which is Sun's implementation detail. I need to define a couple of more trait bounds because we are in an HTTP server. Futures need to be sent across multiple threads, possibly. If you are sending those futures across threads, then maybe you want to have static lifetimes, which is typically for HTTP servers. I guess Rainer mentioned something like that in his Rocket talk from a couple of years ago, actually. So yeah, I needs a couple of trait bounds to work, but that's it. You're getting lots of error messages if you don't have those trait bounds, so we'll know. So also the future from this service needs to be sent. And I guess the response just needs to have debug and display because I have a couple of log lines in there that I want to use. So this is all related to the service that I want to call. So coming from the HTTP service, this is the next one. The types, the associated types are also very different. So the response now is not just what comes from my own function, from my own handler function. Since I'm in HTTP land, I need to provide an HTTP response with the body again. So this is a type that comes now from Hyper. And it's my duty in this layer that I wrap what's coming from this service to produce a response, an HTTP response with the body. The error is the same. I guess in this implementation, I just use the anyhow error instead of writing it on my own. But I can use the same error. And here I have a future, which is a boxed future with static lifetime and the result again. So this is a little bit long. I'm going to tell you in a second why I need a boxed future. Because I want to do a couple of things with the response that can't be done as easily as we've seen in the last example. So I need a boxed future. I'm going to tell you in just a second. It's very important to get those types right. Those types will make or break your entire implementation, and you are getting error messages from hell. So this is if you're getting one trait bound wrong. I guess here I got I forgot the send trait, the send trait marker to add as a trait bound. Then you're getting towered, which means you're getting pages of error messages with all the generic jazz, and especially if you're wrapping things into each other. It's generics and generics and generics and generics, and one little implementation might not work. Boom, that's it. I hope that those error messages will get a lot better to read the moment we have async traits within the language. So especially all the boxing and pinning, I guess, will be easier because we're not only trying to return futures, but we can say, well, this is an async function that returns a result, and we can get the future terminology out of it, and that should already make it easier. So hopefully, Nick Cameron was at Rust Linz and spoke about that, and I asked him this question. He said, yes, that should be easier, hopefully. So really looking forward to what the async working group is doing. Alrighty, let's look at the implementation, at the call function. Here are a couple of things that are very, very different. What we want to do is we want to call the service somewhere within our code, take the result, and then produce an HTTP response. And because we are calling this asynchronous function somewhere in the middle, we need to create a future that doesn't move in memory anymore. This is what the box pin does. This is, I guess, a talk entirely on its own, and I guess Without Boats did one at one of the Rust comps, which you can find in the Rust channel, all about pinning and boxes. We're not doing this here today. Just know we are doing all the jazz and having boxed futures and boxed pin, etc., to be able to do something before we call the inner service and to do something after we call the inner service. This is why we are doing that. First, we are cloning the inner service. Clones are pretty cheap. You don't clone that much. So memory-wise, it's not that big of an operation. But the problem is that your async, so your future might already be polled when the clone is not ready yet. This is something that I've read in the documentation just recently, which means that this line here, make sure that your clone is ready by replacing the clone with, or the actual inner service with the clone, and then you can work on the actual inner service. That's just this technique to make sure that the clone is ready and that you can work on it. Then we are pinning, so we are creating an async block. We are pinning it in memory so that it can't move anymore. We prepare the request. So this is the request object, which is an actual HTTP request. What this function does is that it extracts all the information that we need and puts it in some data, which is assert a value again. Then we call the inner service, wrapping the assert a value in our event structure again, await that. And once you get the result, either if the result is okay, I'm going to return an HTTP response with a status code okay, and with the result a string. Otherwise, an empty body and an internal server error, so that we can have two different responses that are okay but carry the error value inside the response and not with the Rust error, something like that. And that's the implementation to attach my function to an HTTP server and ultimately to Azure Functions. Okay, that's the implementation of a service. We can use the service, then we can wrap our services within each other. That's fine. Or what's much, much nicer is to create layers. Layers are data structure that work next to services, and you can chain them. So you can say, well, this layer, then this layer, then this layer, then this layer, just like you would have a middleware stack. We are going to see an example just recently, just in a couple of seconds. The implementation is also very similar to all the others. Here we are creating the new service, wrap the inner one via these layer functions. You just need to implement the layer function. The structs can be empty, so there's nothing much to it. And this is for the HTTP parser. This is for the Lambda event parser. Same thing, different names. So just wrapping your service in the Lambda event parser. Okay. How are we going to use that? This is how it's being used in Lambda. They just updated the SDK. They now provide you with a service function, which means that you can take your function and wrap it into a Tower service. So now it's compatible with Tower, with the interfaces that you defined. This is a very nice way to make every one of your functions Tower ready. Then we create a new service builder. First layer is a timeout layer. I don't want my function to run longer than 3 minutes. And I'm using a timeout layer here and the timeout service here because I want my implementations on Azure Functions and Lambda to work similar. And in Lambda, I can configure a timeout per invocation. And I guess I can't do that with an HTTP server in Azure Functions. I want them to work similar. This is why I use the timeout layer here. Then I have my Lambda event layer, and then I have my function. And I run it. That's it. So this is being wrapped into a service, and the Lambda event layer takes what comes from above, which is a Lambda event, transforms it into something that the function can read, and then we bubble the values up again, and we're done. Fantastic. This is how we are doing it in Azure Functions. We are creating an HTTP server. I'm using here Hyper. I'm not using a framework, just Hyper as it is. I have a port key, the function's custom handler port. I let it listen on localhost. So this is you have to listen to this port if you want to attach it to Azure Functions. This is how the function host is communicating with your server. Then spin up a server. And again, I'm also building up a couple of layers. So I have this make service function, which is a constructor, a factory services, the service for services, or a service made out of services. I have the service builder again, the same timeout layer. I even included a log layer because I wanted to have some log output. Then my HTTP parser layer, and then again the service function, just like in the other example, with my handler function. And there you go. Boot up the server and serve all my services, and that's it. So the cool thing is everything here with the service builder and my service function, that's all the same thing. No matter if I'm on Azure Functions or if I'm on AWS Lambda. The only thing that I need to change is the HTTP parser layer for Azure Functions and the Lambda layer for AWS Lambda. And then my app works on both serverless architectures. Fantastic. This is what I wanted to achieve. Cool. And that's that. So what's in the box with Tower Services? It's not only the trait. It's not only the service trait that you can implement. There are a couple of things in there that are really, really important if you want to create networking applications, especially if you think about Kubernetes and Kubernetes clusters. I guess the Istio service mesh, if I'm not mistaken, uses Tower a lot to implement all the networking connections that go between your Kubernetes pods. And you can do things, that help you for an HTTP server, for example, like having timeouts or logging, request limiting, buffering, throttling, but also you can have stuff like load balancing, load shedding, etc. I work at the monitoring company. What I created a little layer that produces OpenTelemetry spans, so I can have for all my requests a little bit of default telemetry already hooked up to our monitoring solution. I just need to include this one layer, and I'm done with it, and get at least some monitoring. So that was really nice. As for the ecosystem, Hyper is based on Tower. So I guess even the whole Tower concept originated from Hyper, if I'm not mistaken, because I could see things like the make service function and the service function first in Hyper, then in Tower. So now you're using Tower directly. And yeah, if you spin up a Hyper server or Hyper client, you are creating services that are based on Tower. So since Hyper is based on Tower, so it's every web framework that is based on Hyper. Guess what? And in some, you can see that, for example, Exum. So Exum makes really, really good use of of Tower services. They are not hidden. You can see them and you can add just layers as you like. If we have a little bit of time, I'm going to show you a little example there. So yeah, this if you're saying Hyper applications or Hyper-based applications, you're basically saying Tower anyway, which means if you have a set of really nice reusable services, which are probably very generic, then you are good to go for every Hyper application that you're doing. A couple of things to read. I have a couple of examples that you can find on GitHub. I would also invite you to read the Tokyo blog about inventing the service trade. This is a blog article that was released last year, which really shows why the service trade is important and why it is like it is. And you can find all the slides and all the information that you see here today tomorrow on my blog, or if you're watching the video on the Rust channel, it's already there. So I'm definitely putting up the slides before I'm putting up the videos. Okay. Do we have a couple of more minutes? Because then I have another example. I just want to click through so that you know how a timeout service, for example, is implemented. And I'm going.
Stefan, I think you are good to go. It's super interesting, and I think many people will be happy to see some examples.
Cool, great. So I'm going to boot up another application. Give me just a second. Boom, boom, boom. So, and there you go. Alrighty. So let me move it around. Let me make it a little bit bigger. No, that's the wrong one. I'm super sorry. I have 7 VS Code windows open, so and all look rusty. It's that one. It should be that one. Okay. Yeah. Okay. Now I need to find it here. Okay. Let's make it a little bit bigger. So what I did here, I created an Exum server. I don't know if we've done Exum on this channel already, but we should. So it's a fantastic new framework, I think, and maybe we can get some of the core team, because I guess somebody from Denmark develops on Exum. This would be very interesting for Rust Linz. I can define a couple of routes, and then I'm going to, I have a couple of get handlers here where I say the root uses this handler, the timeout, I'm taking this timeout variable, and it goes into the timeout handler. And the idea is that I have, where's the timeout handler? It's here that I sleep for the number of milliseconds that I get in. So if I'm saying localhost /1000, I'm waiting 1000 milliseconds. Localhost /100, I'm waiting 100 milliseconds, stuff like that. And if this number of milliseconds is lower than my timeout limit, then I'm writing out I made it. But here I have, those are my routes, and then I'm having a logger layer. Again, I want to log my stuff, and I'm having a timeout layer that waits for 300 milliseconds, which means after 300 milliseconds, this future resolves, this future is in poll ready, which means that the entire service is in poll ready, which means that the actual future from the timeout path is being cancelled. Yeah, and I'm handling the error in here. And so if I curl it with, let's say, 500, you can see here, it's processing get 500, and it's an elapsed error, so it's canceling the error. If I say, let's do 100, here I'm getting made it, and my logger also said, well, I'm processing it, and it has been processed afterwards. So this is how it should work. Let's look at the timeout layer. This is the timeout layer. The same thing. It's wrapping the timeout service. So this is what it does. But it has another parameter, which is the timeout itself, which is a duration. Let's go into the timeout service. It has dinner service. It has timeout as duration. Couple of constructor functions, conversion functions, and this is the whole implementation. And you can see it needs to work on requests. Fantastic. It has the errors. This is nice. You can use any error that you like as long as it can be converted into the box error from this thread. This is a very nice pattern. So this makes compatibility pretty great. If you say the only thing that I need to provide is something that can be converted into the actual error instead of trying to align all your errors or all your results. I have the poll ready. It's either in pending or it's in ready. If I have an error, it's being mapped. And here's the call. So I have two futures. One is the response if I call inner. The other one is the sleep future. And then I'm putting both into the response future. Going into the response future, if I'm looking at the poll, the only thing that it does is, well, let's see if the actual future is ready, if the actual request is ready, then check the sleep function. And if it's ready, then return an error because, well, the timeout has happened, the timeout has elapsed, and the other one is just being cancelled. So this is what happens here. And that's not that much of code. So it's a couple of lines with arguably some async magic that you need to get used to. But with that and this great abstraction of a service that takes stuff from above and puts it down to the next one, you can really compose fantastic network applications with it. So and that's about it. With that, I want to say, here we go. Thank you. Thank you, and I'm open for questions.
Awesome. Thank you very much. Thank you, Stefan. Super interesting talk. I learned a lot. Yes, and I definitely think we need this topic in Rust Linz. We should schedule it for one of the upcoming meetups, maybe in autumn or winter. We should put that on our to-do list.
I try to reach out to them. I guess it would be nice to have the Tokyo Exxon folks.
Oh yes. Let's ask them. Let's ask them. Okay. We have two questions. I think the first one got already answered from you. We have the question: are there any good tower tutorial series? The user doubts that he or she can figure it out by himself or herself.
Yeah. So I understand the doubts because I had them myself, and it's not that easy because the documentation is great. There's a lot of examples out there, especially the AWS Lambda folks pushed a lot into the direction to make Tower much more prominent in their code, which means that you get more examples that you can kind of figure out what to do. I haven't seen a tutorial series. I haven't seen there's one video tutorial out there, like a live stream for about 2 hours that takes care of that, but not like video tutorials or written tutorials. I want to write one, but as everything, this is one of the many side projects that I hope I will get done sometime this year. But everything that I just kind of figured out, I want to write it down for others to share. So maybe you get one for myself, or the team is working on one. But right now I don't know of anyone myself. Yeah.
Okay, great. The second one comes from Melvin. You can read the question. I will repeat it for those who are listening. Is that everything that Tower does? It seems like it is a really lightweight library, not much code. I got the same impression. What would you say?
Yeah, so the thing is, the service trait is really very lightweight. This is by design. So this is what they wanted. They wanted to have this incredibly flexible trait that, as you can see, you can take and put into all the applications and are done with it. And there's, of course, the whole layer mechanisms so that you can wrap your services much easier. So that's all great. And the other, at core, it's not more than that. But all the implementations, like I've just seen you one of the easier implementations, like the timeout is very easy to grasp, to see what's going on, because everybody can figure out what the timeout does. If it goes into the load shedding implementations or into the load balancing services, there's a lot of knowledge in there.
Yeah,
and there's a yeah, and this is great. It comes with this whole box of good stuff, so you can get started with your own networking applications if you need to do reliable networking applications. But this is where it doesn't get lightweight anymore, and this is also where things need to align much more between services, and all that knowledge is within the library. So I would say it's definitely not as big as let's say Tokyo, which is the Swiss Army knife of async programming, but being the foundation for things like Hyper or Tonic, there's a lot of stuff in there already, and it gets complete with Hyper, it gets complete with Tonic.
Okay, super. Cool. Very interesting. Thank you very much.
Right.
Let me check the questions. I think you answered all the questions. Last question from my side. Can you please share the slides on Discord? That would be awesome.
Yeah, so I will do them today. I will push everything up that I've shown you today. Yeah.
Nice, because I think you had also some interesting links to GitHub and maybe videos and so on, and that is super easy if you can just download the PDF and that's it. And I think we already shared the link to our Discord server for people who are watching that on YouTube, either live or the recording. So feel free to join our Discord server and you can grab the slides from there, and you can also ask a question, get in contact with us, whatever you want to do. So, Stefan, thank you very much. Thank you very much for taking the time to prepare this awesome talk. We already announced, it was our pleasure. We already announced that next time we will hopefully, if everything goes nicely and smoothly as we plan it, crossing fingers, at the beginning of September with an in-person meetup. Hopefully it will work out.
I'm really looking forward to that. Let's hope it becomes reality, especially for our star speakers. I'm so excited. I don't want to spoil it because it's great. It's like all the planets align and the entire world comes to Linz. Kind of. So it's a great thing, though. One thing that is fantastic in Discord, people from Slovakia, I guess, also want to join for the next in-person meetup. So people from all around Europe and possibly the world are coming to this one. So I'm really looking forward to that one.
Nice. I really enjoy that. When I took a look at the comments of YouTube at the beginning of this meetup, I saw, for instance, a greeting from Israel. I saw a greeting from Brazil here. I saw a greeting from India here. And that is really amazing. Fantastic. And I think I speak for both of us that we have to say thank you for awesome audience, for watching the videos live, for asking questions, for watching the videos on our YouTube channel. You are awesome. And this is what motivates people like us who organize meetups, because just doing it for our own would be boring with everybody coming to the meetups. That is really
thank you for the last 2 years, basically. So it's been a fantastic ride with you, and we are so happy that you all enjoy watching Rust Linz with us and being part of this.
Okay, and I think with that, we go right into the evening. Enjoy the rest of the evening. To everybody in the audience, enjoy, and we'll see each other at the beginning of September.
Alrighty, bye-bye.
Bye.